Now let's talk about a refrigerator, a heat pump and a heat engine. We'll start by understanding the concept of heat engine, and we have already done this, so I'll just summarize the whole concept of heat engine and then we'll compare these two things, as one you can say device. There's a very minute difference between a heat pump and a refrigerator as compared to heat engine. Now let's start with the heat engine. So this is the heat engine, which is exchanging heat between T1 and T2. These are the two TERs, and I can assume that T1 is higher than T2. And this is true for all these three devices: a refrigerator, a heat pump and a heat engine. Now in this case, Q1 is the absorbed heat from the source. It goes into the cyclic heat engine. Some heat is rejected and you get some work output or net work output from this device. Now the performance analysis of a heat engine. Now this is a very important word, that is performance analysis. Let me write it down here. Performance analysis. How good is your device performing? For a heat engine, the performance analysis is done with the help of a parameter named as efficiency. So we calculate the efficiency of a heat engine, and the efficiency is given as the ratio of the net work output upon the heat input, and this is equal to 1 minus Q2 by Q1. So this is how we analyze the performance of a heat engine, that is in the terms of the efficiency of the heat engine. Okay, and we always know that this is a value which is less than 100% or less than 1. Now, if you talk about a refrigerator and a heat pump as or in comparison to heat engine, well, heat engine is, you can say, an energy producing device. It is an energy producing device. It produces some net work output, whereas a refrigerator and a heat pump, both of them are energy consumers or energy consuming devices. Alright, so it uses work as some input. So this schematic, which is having some heat being transferred from T2 to T1 and which has some work as input, can be either a refrigerator or a heat pump. Okay, so right now I'll just write down RE as the refrigerator or heat pump, that is the HP. Now what is the difference between this schematic being for a refrigerator or for a heat pump? Because for both of them the schematic would be same, but what is the differentiation between the two? Okay, and that differentiation comes with the performance analysis parameter for both of them. Now the performance analysis for a refrigerator and a heat pump, this is done with the help of a parameter known as the coefficient of performance. The coefficient of performance is very commonly known as the COP of the refrigerator or of the heat pump. Now the general definition of COP is equal to the desired effect upon the work input, and the difference of this schematic, whether it is for a refrigerator or for a heat pump, comes in the shape of the desired effect. So the desired effect for a refrigerator is different and the desired effect for a heat pump is different. Okay, let's talk about it. Now let us first of all assume the case of a refrigerator. Now what do we expect from a refrigerator? That is, it should cool this space, so maximum cooling is required over here. Now how do you produce cooling? By absorbing maximum amount of heat from this space. So we are not concerned about how much heat is being rejected. We are only concerned about how much heat is being absorbed from this space where cooling has to be produced. Okay, so the desired effect is cooling, and cooling is directly proportional to the amount of heat absorbed. So we are concerned with the heat absorbed. So I will write down that the COP of a refrigerator is equal to desired effect being the heat absorbed upon the work input. So this is the COP of a refrigerator, where the desired effect or the thing or the parameter to be focused upon is the amount of heat being absorbed, because that is proportional to the amount of cooling you will have in this area. Okay. On the other hand, and on the same lines, if you talk about heat pump, a heat pump is something like a heater. Now in cold areas, okay, just assume this is your room and this is the outside of the, or you can say this is the outside conditions out of your home, right? So let us say this is at minus 10 degrees Celsius and this is a room which has to be maintained at 28 degrees Celsius, okay, to keep you nice and warm. Now what your heat pump will do, it will pick up heat from the minus 10 degree source. Some energy would be added with the help of the work input, and you would have the heat being thrown in your room, which will keep your room warm. So this is the function of a heat pump. Okay, now in heat pump, what is the parameter of analyzing the performance? That is the amount of heat rejection, because we are more concerned with the amount of heating that is being produced in your room. What is the amount of heat being absorbed is is something I cannot control. Okay, I can just add the amount of energy in the form of work input, and the thing that I'm concerned with is the heat rejected into your room. So the desired effect for a heat pump becomes the heat rejected upon the work input. So this is a differentiation between a refrigerator and a heat pump. Now, if you talk about the relationships, let me write down the heat engine here first of all. Okay. Then let us write down the refrigerator or a heat pump. Right. Now, Q1 is the heat absorbed. Okay, and Q absorbed is denoted as heat absorbed in the case of a refrigerator or a heat pump. Okay, now this is done from T1 and this is done from T2, and we know that T1 is higher than T2. Q2 is the heat rejected, and this heat rejection is done to a heat sink at temperature T2. And if you talk about a refrigerator or heat pump, the heat rejection is Q rejected, which is heat rejected or heat rejection, which is at temperature T1. Now, you have some net work output from this and you have some net work input for this. If you go back to the diagrams, okay, this is the system in the case of a heat engine. Okay, now whatever that comes into the system, this is the input to the system, that is equal to the output of the system. So I would say that Q1, which comes in the system, is equal to W net plus Q2. So this is the relation between Q1 net work and Q2 for a heat engine. Okay, so let me write it down here. So this is equal to Q1 minus Q2, or I can say that Q1 is equal to W net plus Q2. Okay, this means that the heat absorbed is greater than the heat rejected for a heat engine. Alright. Okay, now let's look at the refrigerator or the heat pump schematic. Now this is the system. So these two things are the input to the system, that is work input plus the heat absorbed, and what comes out of the system is the heat rejected. Alright, so the relation between the three terms becomes Q absorbed plus work input is equal to Q rejected. So this is the relation. Okay. And this is true for both a refrigerator and a heat pump. Now in this, I can say that the heat rejected is greater than the heat absorbed. So this is a very big difference between a heat engine and a heat pump or a refrigerator. Right, so you should note down and understand these or this analysis between these three devices. Now, let's compare the COPs of a refrigerator and of a heat pump. Now that we know the relation between all these three quantities, so let's have a look. Now, Q rejected, I know it is equal to Q absorbed plus the work input, isn't it? Let us divide this whole equation by work input. So we would get Q rejected upon work input is equal to Q absorbed upon work input plus 1. Now from this I can say that this is the COP of a heat pump and this is the COP of a refrigerator. So it becomes the COP of a heat pump is equal to the COP of a refrigerator plus 1. So this relation tells us that the COP of a heat pump is greater than the COP of a refrigerator by unity. Okay, so this is the relation between the COP of two devices, and this finishes the video on the differences and the analysis and the performance analysis of a refrigerator, a heat pump and a heat engine. Now in the next video we talk about the equivalence of KP and Clausius statements.